Hello, I'm Pratibha is working as a assistant professor in the Department of Electronics and Communication Engineering of Government Engineering College, Ramnagar. This I'm going to welcome all of you to this lecture series on digital image processing for seventh semester. This video lecture is a part of LMS under Department of Collegiate and Technical Education. So today I'm going to discuss enhancement in spatial domain process. So before commencing, what is a spatial domain? So let us see what and all the topics I'm going to discuss in this particular session. They are background, some basic intensity transformation functions like image negatives, log transformations, power law transformations, piecewise linear transformation functions, and this session will be ended with the discussion of multiple choice questions. So before commencing what is the background of spatial domain process, let us see what is the necessity of the image enhancement. Then we will see that image enhancement techniques fall under two categories, spatial domain and other one is the frequency domain. So now let us see that what is image enhancement uh, technique. It is a technique of processing an image to enhance certain features of the image. Some applications may demand that our input image is noisy, so we want to reduce the noise so that image becomes better visuality. So reduction of this noise or removal of this noise from the image is also a part of, or it is a form of a image enhancement. In many cases, we have found that the images which are captured by image capturing devices, for example, camera, they are very darkened. An image may become very dark because of various reasons. So, for such kind of applications, the image enhancement technique may need to increase the contrast of the image or to increase the intensity of the image. So, for that kind of application, we will have some other type of image enhancement techniques. We want to process an image so that the result becomes more suitable than the original image for certain specific applications. So what is the need of the image enhancement? The processing techniques are very much problem oriented because different kinds of problem demand enhancement of different kinds of features in the image. So obviously the processing techniques will be application dependent. Naturally, a technique which is best suitable for one kind of application is not best suitable for other kind of application. For example, if a technique is more suitable for processing the X-ray images, may not be the best for enhancement of the microscopic images. So this is broadly what we mean by enhancement of the images, and obviously these are application dependent. So the categories of the image enhancement, as already said, there are two. One is spatial domain process and the other one is the frequency domain process. The spatial domain process where uh, the processing will be done or transformation is done directly on the pixels of the image. Other category, of course, the frequency domain, where the first we have to take the Fourier transformation of the image, then whatever is the Fourier transformation coefficient, we need to modify the those Fourier transformation coefficients. So this is exactly the background. So the general form of the spatial domain process is expressed by the equation g of x comma y is equal to t of f of x comma y, where f of x comma y is the input image, g of x comma y is the processed image, and capital T is an operator on f defined over some neighborhood of x comma y. So we're going to discuss, for example, we'll take an 3 cross 3 neighborhood about a point x comma y in an image in the spatial domain, the neighborhood from pixel to pixel in the image to generate an input image. Now, look at this particular figure. Here, you will find that we have taken a rectangular image F, image F. So this outer rectangular represents the image F, and within this image F, we have taken a pixel at a particular location x comma y. So this is the pixel location x comma y, and the neighborhood of the point x comma y, as we said that it is usually a square sub-image around the point. So this shows a 3 by 3 neighborhood around the pixel point x comma y in the image. Now, what happens in case of point processing? We said that this operator T operates at point x comma y, considering certain neighborhood of the point x comma y. And in this particular case, we have shown neighborhood size is of 3 by 3, point 3 by 3 neighborhood, and depending upon the application and the image, we can go for considering the other sizes like 5 by 5 or 7 by 7 and so on, depending upon the image and the type of the operation what we want to have. So now in case of point processing, like the size 1 by 1, that is considered is of size 1 by 1. So the neighborhood size at a point in case of point processing is of size 1 by 1. So that means this operator T now works on a single pixel location. So it works on only that particular pixel location xy, and depending upon corresponding location in the processed image G, uh, it does not consider the, so depending upon the intensity value at that location xy, it determines what will be the intensity in the corresponding location in the processed image G. It does not consider the pixel values of its neighboring location. So in such cases, we can write the transformation function in the form S is equal to some transformation T of small r, where this r is the pixel transformation, sorry, this R is the pixel value in the original image, and capital S is the pixel value in the corresponding location in the processed image G. So, where T is nothing but transformation function T. So, overall for the size 1 by 1, we're going to have the transformation function, which is given by S is equal to T of R. So where S represents, S is nothing but intensity of the G at X comma Y. Uh, so which is here, this will be explained with an example where these transformation functions can be put in the form of these two figures. So, in this particular case, the first figure shows a transformation function where you find here in this case along the x-axis or along the horizontal axis, we have put the intensity values or of the original image, and along the vertical axis we have put the intensity values of defined pixels in the processed image G, and obviously they are related by S equal to T of R, and the transformation function is given by this particular curve. So this is our T of R. This is our T of R. And in this particular figure, as it is shown that uh, um, the point, so the pixel values near the zero has been marked as dark region. So it is quite obvious that in an image, if the intensity values of the pixels are near about the zero, that is very small intensity values, those regions appear as very dark, and the intensity values which are higher in an image, those regions appear as lighter region. So this first one, the first transformation function shows that in this particular um, the range, very narrow range. You can observe here, it's a very narrow range of the intensity values in the original image is matched to a wide range of the intensity values in a processed image G. And effectively, this is the operation which gives enhancement of the image. In the second figure that we have shown here, you find this particular transformation function says that if k, consider if say this is some intensity value, say k, so for all the pixels in the input image, if the intensity values are less than the k, then in the processing image, the corresponding pixel will be replaced by a 0, whereas a pixel where the intensity values is greater than the k, the corresponding pixels in the processed image will be the maximum value. So the this second particular transformation operation, it actually generates a binary image consisting of only the low values and the high values, and this particular operation is known as threshold operation. So uh, next slide, all about some of the basic intensity transformations. The values of the pixels will be noted, that is R before the processing and S after the processing. So digital is nothing but the values of the T typically stored in a one dimension array, and the mappings from R to S implemented via table lookups. As we know, the basic intensity transformation functions like negative transformation, identity transformation, logarithmic transformations like log transformation, inverse log transformations, and the piecewise linear transformations, and even the power law transformations. So all this will be scaled into a single range, or all that will be fit in the range as shown in this diagram. So first we're going to discuss what will be the basic intensity transformation. So start with the image negatives. Um, so negative of the image with intensity levels in 0 to L minus 1 obtained by S is equal to L minus 1 minus R. So how the negative of an image can be obtained by using this expression. So S is equal to L minus 1 minus R. So in this, this is what the first one that we'll consider is point processing technique, which will call the negative image. Now, in many of the cases, the images that we get, they contain white or the gray level transformation embedded in black pixel or uh, very dark pixels, and the nature of the information is such that we have very few white or gray level information present in a white background, which is very much dark. So in such cases, finding out the information from the images, from the raw images, input images, becomes very difficult. So in such cases, it is beneficial that instead of considering the raw image, if I just take the negative of the image, that is all of the white pixels that we had in the image are the larger intensity values that we have in the image. You make them darker, and the darker intensity values, you make the lighter or brighter. So in effect, that we get is a negative of an image. And within this negative image, we will find through a result that visualization or extracting information which we want will be more convenient that than in the original image. So the kind of transformation that we need in this particular case is shown in this figure. So here, we considered that a digital image that we are considering that will have capital L number of intensity levels representation are represented from 0 to capital L minus 1 steps of 1. So again, along with the horizontal axis, you can see here, along with the horizontal axis, we have put the intensity uh, values of gray level, values of the input image, and along the vertical, you can see here, along the vertical axis, we have put the intensity values of gray level, values of the processed image, and this corresponding transformation T now can be represented as S is equal to T of R, which is nothing but L minus 1 minus R, L minus 1 minus 1. You can see here S is equal to L minus 1 minus R. So you find that whenever R is equal to 0, whenever R is equal to 0, then S will be equal to L minus 1. Then S will be equal to L minus 1. Okay, whenever R is equal to 0, then S is equal to L minus 1. So which is actually the maximum intensity value within our digital image. And when R is equal to capital L minus 1, the S and is the maximum intensity value in the original image. In that case, S will be equal to 0. Then S will be equal to 0. So uh, intensity value in the processed image and the minimum intensity value in the processed image will be converted to maximum intensity value in minimum intensity value in the original image will be converted to maximum intensity value in the processed image. So, what in effect, what we are getting is a negative of the image, and graphically, this transformation can be put in the form of figure. So here you find this transformation is a straight line with a slope of minus 45 degree and passing through the point 0 L minus 1, that is 0 to L minus 1 and L minus 1 0 in this RS plane now. RS plane. Okay. So now let us see what is the kind of result that we will get by applying this kind of transformation. So here we have shown two images. On the left hand side we have digital mammogram image, and on the right hand side we have the negative of this image, which is obtained by the transformation and that we have just now discussed. So you find that in this original image, we have some white, uh, like white tissue like grains, and here is a white patch which indicates a cancerous region, and to these grains corresponding to the issues, um, corresponding to the tissues, they are not very prominent. I mean, it is very difficult to make out which is what in this original image. Now, if I take a negative of this particular image, from the right hand side, um, we have got this negative. So here you find that all the darker regions in the original image has been converted to brighter, and in the pre-processed in the processed image, and now it is very convenient to see the information we can get from this negative image. And this kind of transformation, the negative transformation, is very useful in medical image processing. And as this is just an example which shows the understanding of this particular digital mammograph image, the negative transformation gives us much more information than what we have in the original. And we said this may this is the transformation which is the best suited for the particular operation. But this is transformation may not be the best transformation for other kind of transformations. So this is uh, actually the operation suited for this particular here. Some other form of applications where we need to reduce the dynamic range is, say for example, I have an original image whose dynamic range is so high that it cannot be properly reproduced by our display device. So normally we have a gray level display device or a black and white display device which normally uses 8 bits. That means it can display intensity levels from 0 to 255. That is total of 256 different intensity levels. But in the original image, if I have a minimum intensity values of say 0 and the maximum intensity value of say a few thousands, then what will happen that because the dynamic range of the original image was very high, but my display device cannot take off such a high dynamic range. So the display device will mostly display the highest intensity values, and the lower intensity values will be in most of the cases suppressed, and by that kind of image that we will get usually is something like this. So here you find on the left hand side, we had shown an image. This is basically the Fourier transformation, the DFT quotients of certain image. So on the left hand side, we have shown an image, the Fourier coefficients, and here you find that only at the center we have a bright dot. Uh, and outside this image is mostly darker or mostly black, but actually there are a number of intensity level between the zero and the minimum, that is zero, but between this maximum and the minimum levels, but which could not be reproduced by this particular device because its dynamic range is very poor. On the right hand side, we have shown the same image after some pre-processing, that is after reducing the dynamic range of the original image by using the image enhancement techniques. And here you find that in the processed image, in addition to the bright spot, at the center, we have many other coefficients which are visible as you move away from the center. So here, our application is to compress the dynamic range of the input image and the kind of transformations which can give us this dynamic range compression is a transformation of this form, which is a logarithmic transformation, or in short, that can be called as log transformations. So here again we assume that small r is the intensity of a pixel in the original image, and the capital S is the intensity of the pixel in the processed image or the output image, and the relation is S is equal to T of R, which is equal to C log into 1 plus modulus of R, where C is the constant. That is, S is equal to C log of 1 plus R, where C is a constant. This constant has to be decided depending upon the dynamic range of your display device and the dynamic range of the input image which is to be displayed, and then log of the 1 plus modulus of R is taken, because otherwise whenever R is equal to 0, that is an intensity level in the input image is equal to 0 log of 0 is not defined. So take care of that. We take 1 plus modulus of R, and if you take C log 1 plus modulus of R, that gives a complete completion of the dynamic range, and the image can properly displayed on a display where the dynamic range is limited. And so this is a pre-processed image. We have taken the Fourier spectrum, what I explained, and this is what the result of applying the log transformation with C is equal to 1 after that is after processing the image. So next transformation for our discussion is power law transformation. That is, it is a similar such operation like logarithmic transformation. Again, for enhancement, that can be used is what we can call as a power law transformation. The power law transformation can also be called as a gamma transformations. The power law transformation is normally used for different imaging devices. It is used for image capturing devices. It is used for image printers and so on. In case of power law devices, the transformation function between the original image intensity uh, and the processed image intensity is given by S is equal to uh, T of R, which is nothing but C into R to the power gamma. that is C into R to the power of R. Okay. So in this plot, we shown this plot for a different values of gamma, where uh, yeah, where the C is equal to 1. So you find that for value of the dynamic range, sorry, gamma which is less than 1, this information or transformation function usually towards the lowered intensity from 0.04 to 25.0. The lowered intensity side, it expands dynamic range of various small intensity range in the input image, whereas for a higher intensity side of the higher range of the input is intensity is matched to a lower intensity of the intensity values in the processed image. And the reverse is true for the values of gamma which are greater than 1. Now this kind of transformation, the exponent, uh, is conventionally uh, represented by symbol gamma, and this is why this transformation, this kind of correction is also known as gamma correction. And this kind of processing is used, as I said, for different types of display devices. It is used for different types of printing devices. It is used for different types of capturing devices. The reason is all those devices mostly follow this power law characteristics. So if I give an input image, that will be converted by power law before the image is actually produced now. So compensate for this power law which is introduced by the device itself. If I do the reverse operation before and then the actual image that I want to display, that will be displayed properly. Say, for example, uh, in this case, CRT display, the relation between the intensity to voltage that follows the power law with the value of gamma, which varies normally from 1.8 to 2.5. So if I use the value of gamma equals to 2.5, and if I come to this particular figure, then you find that gamma equal to 2.5. This is the curve, or the or this is the correct, this is the curve. Gamma is equal to 2.5 curve. This is the correct transformation function that will be used. So whichever image I want to display, the device itself will transform the image using this particular curve before displaying the particular image. And as the curve shows, that image will be displayed will normally be darker than the original image that we intend to display. So what you have to do is, we have to take some corrective measure before giving the image to the CRT for the display purpose. And because of this correction, we can compensate this power law so that our image will be displayed properly. So coming to this slide, you find that here we have shown an image which is to be displayed, and the uh, image is on the top left corner. The monitor has a characteristics of power law. It has power law characteristics which is given by S is equal to R to the power 2 to the power 2.5. And as we said that because of this power law characteristics, the image will be darker, and which is obvious that the image as displayed on the device is given on the right hand side, and you will find that this image is darker than the original image, right? Okay, so to compensate for this, what I do is before giving this image to the CRT for display, you go for a gamma correction. That means you transform the image using the transformation function S equal to R to the power of 1 upon 2.5. So by this transformation, and if you refer back to our power law curves, you will find that original image now becomes brighter image, that is lower ranges in the input image has now been mapped to a larger intensity range in the processed image. So as a result, the image has become brighter. Um, and when this brighter image is given to the CRT for display operations, the monitor will perform its characteristic power law. What is S is equal to R to the power of 2.5. And because of this characteristics, the earlier correction, that gamma correction what we have incorporated and gets nullified, and we get the image, and now we find the right bottom. This is actually the image now which will be displayed on the CRT screen, and this image now appears to be almost same as the original image we want to display. So this is a sort of enhancement, because if I do not use this kind of correction, then the image that we are going to display on the CRT screen, that will be distorted image. But because of the power law correction or the gamma correction, as it is called, the image that we get on the CRT screen will be the same, almost same as the original image that we want to display. So now this kind of power law transformation, it is not only useful for image devices like CRT, display, or image printer, and so on. Similar power law transformation can also be used for enhancing the images. Now, the advantages that you get in case of power law transformation is that the transformation curve gets various shapes depending upon different values of gamma, and as we shown in our previous slides, so the value of gamma is less than the 1. Then on the darker side, the lower range of the intensity values will be mapped into a larger range of the intensity values in the processed image. Whereas on the brighter side of the larger range of intensity values will be mapped into a lower range of the intensity values in the processed image. And the reverse is true when gamma is greater than 1. So by using different values of uh, gamma, I can have different power law transformation, and as a result, I can have is a controlled enhancement of the input. So this is one more example. When we're going to apply the power law transformation, this is actually the magnetic resonance image or MRI of a fractured human spine. This is a first diagram, and the B, C, D, all the three diagrams, the result of applying the transformation in uh, equation. So this is also useful in the medical. So our next type of transformation function is a piecewise linear transformation function. Piecewise linear function can be arbitrarily complex. Specification requires much more user input. So there are two types of piecewise linear transformation functions. One is contrast stretching, and other one is intensity level slicing. So now let us see that what are the other kind of image enhancement techniques that we can have. The next image enhancement technique is again a very simple enhancement technique that we are going to discuss, is called the contrast stretching. So why do we need such contrast stretching? You might have found that in many cases, the images that we get from an imaging device is very dark, and this may happen because of various reasons. One of the reasons is when you have taken the image of the certain object or certain scene, the illumination of the object or the illumination of the scene was very poor. And that means the object itself was very dark. So naturally, the image has become very dark. The second reason why an image may be dark is the dynamic range of the sensor on which you are imaging is very small. And now what I mean by dynamic range, it is the capacity of the sensor to record the minimum intensity value and the maximum intensity value. So the difference between the minimum intensity value and the maximum intensity value is what is the dynamic range of the sensor. So even if you scene is your scene is properly eliminated, but your sensor itself is not capable of recording all those variations in the scene intensity, that also leads to an image which is very dark. The another reason which may lead to dark images is that when you have taken the photograph, maybe the aperture of the lens of the camera was not properly set. Maybe the aperture was very small, so that very small amount of light was allowed to pass to the lens of the imaging sensor. So if the aperture is not properly set, that also leads to an image which is very dark. So for such dark images, the kind of processing techniques which is very suitable is called the contrast stretching operation. So now let us see what is the kind of dark image that we can have here. We show an image which is low contrast image. So here obviously you find that the contrast of the image or the intensity of the image is very poor, and overall appearance of the image is very dark. And the purpose of the contrast stretching is to process such image so that the dynamic range of the image will be very high, will be quite high, so that the different details in the objects present in the image will be clearly visible. Uh, so now a typical transformation which may be applied for the contrast stretching operation is shown in this particular figure. So here you find that in this particular transformation, we have indicated 2 points. One is R1, uh, um, R1 S1, that um, is the particular point, and the other one is the R2 S2, that is the particular point. Now it is the location of this points R1 S1 and R2 S2 which controls the shape of this transformation function, and accordingly influences upon that what are the defined types of contrast enhancement that we can obtain in the processed image. Now, the locations of this R1 S1 and R2 S2 are very important. You will find that we may R1, if we make R1 equal to S1 and R2 equal to S2, then the transformation function becomes a straight line, which with the slope equal to 45 degree. That means that whatever is the intensity image we have in the processed image, we will have the same intensity level. That means by applying such transformation where R1 is equal to S1 and R2 is equal to S2, in this transformation function that we have said, by applying that kind of transformation, the processed image does not undergo any variation from the original image. For other values of the other combination of R1 S1 and R2 S2, we really get some variation in the processed image. So the values which are mostly used is here. You will find that if I make the other extreme, if I make R1 equal to R2 and um, uh, S1 equal to 0 and S2 equal to L minus 1, then that leads to thresholding operation so that the corresponding operation generates the binary image, which is the processed image. Now for enhancement operation, usually what is used is R1 is less than um, R2 and S1 is less than S2, which gives us transformation function as given in this particular figure. And this transformation function gives uh, generally leads to the image enhancement. Now the condition that R1 is less than R2 and S1 is less than or equal to 2. Now S2. Now this particular condition is very, very important, as you find that if this condition is maintained, then the transformation function that we get becomes a single value transformation function, and transformation is monotonically increasing, so that it is very, very important to maintain the order of the intensity values in the proposed image. That is, an image which is dark in the original image will remain darker in the processed image, and image which is brighter in the original image, that will be point which is brighter in the original image, that will remain brighter in the processed image. But what difference we are going to have is the difference of intensity values that we have in the original image and the difference of intensity values we get in the processed image. That is what gives us the enhancement. But if it is reverse, if the order is reverse, in that case, the processed image will look totally different from the original image, and all the transformation that we are going to discuss except the negative operation that we have said initially, all of them maintain this particular property that the order of the intensity values is maintained. That is, the transfer of function is monotonically increasing and will have the transfer function which is single value transfer function. Now using this particular transfer function, let us see what kind of result we're going to obtain. So have shown in the we have shown an image which is low contrast image as is shown on the left hand side of the particular diagram and of this particular slide. And so this left hand side of the image, what we have got is an image which is a processed image show on the right hand side, and here you can clearly observe the more details are available in the processed image than in the original image. So obviously the contrast of the processed image has become much, much higher than the contrast in the original image. So this is a technique which is called contrast stretching technique, which is mostly useful for images where the contrast is very poor, and we have said that we can get a poor contrast because of the various reasons. Either scene illumination was very poor, or the dynamic range of the image sensor was very, very less, or the aperture setting of the camera uh, lens was not proper, and in such cases uh, we we the such cases the dark images that we get that can be enhanced by using this contrast. The other type of transformation that we can use for enhancement of the image is called intensity level slicing, or we can also call as gray level slicing. So in case of gray level slicing, some application may need that. Application may not be interested in all the intensity levels, but the application may be need the intensity levels only in certain intensity level values or gray level values. So in such cases of enhancement, what you can use is the intensity level slicing or gray level slicing operation. And the transformation function is over here. The transformation function on the left hand side says that the intensity level in the level A to B. Okay, the image will be enhanced, or the other intensity level is the pixel will be suppressed. On the right hand side, the transformation function shows that again within the A and B image will be enhanced. But outside this range, the original image will be returned, and the result that we get is something like this. The first image shows the only the desired intensity levels are obtained, are retained with enhancement all other regions that have been suppressed. The right hand side shows the desired image intensities have been enhanced, but other intensity levels have remained as it is. So this is an example where we have applied the intensity level slicing, considering aortic angiogram. So this is what the aortic angiogram and B, the result of using a slicing transformation of the type illustrated in figure A, with the range of the intensity of the intensities in the upper end of the grayscale, and the figure C, the result of the using the transformation in figure P, with the selected area set to black, so that grays in the area of the blood vessels and the kidneys were preserved. So one more type of transformation under the piecewise linear transformation is bit plane slicing. Here, pixels are digital pixels are digital numbers composed of bits. For example, the intensity of each pixel in a 256 level grayscale image is composed of 8 bits. So here we need to, instead of going for taking the interested intensity levels, we'll go for highlighting the contribution made to total image appearance by specific bits. With the plane one containing the lowest or the least significant order or lowest order bit and of all the pixels in the image, and the plane 8 will have going to have the higher order bit of all the pixels. So here, so this is how the bit plane representation of an 8-bit image, which is shown by this particular figure. So the example for this kind of bit planing can be shown by this particular figure, where figure A, an 8-bit grayscale, gray image of the size of 500 by 1192 pixels, and B is the through I bit planes 1 through 8 with the uh, uh, bit plane 1 corresponding to the least significant bit. Each bit plane is a binary image. So this is what the original 8-bit image and the lowest order bit. So this is what the processed image. So this is how the contributions will be highlighted using the bit plane slicing. Okay. So after discussion of all this, we'll be ending this session one with the discussion of the multiple choice questions. Okay. The first question here, so like this, which expression is obtained by performing the negative transformation on the negative of an image with gray levels in the range 0 L minus 1. So answer mm, is so options S is equal to L plus 1 minus 1, B S is equal to L plus 1 plus R, C S is equal to L minus 1 minus R, D is equal to S is equal to L minus 1 plus R. So answer is S is equal to L minus 1 minus R. So how the answer C is correct one. So here is the explanation. The negative of an image with a grayscale in the range 0L minus 1 is obtained by using the negative transformation which is given by the expression S is equal to L minus 1 minus R. So second question as follows. What is the general form of the representation of the log transformation? So options are S is equal to C log 10 1 by R, S is equal to C log 10 1 plus R, S is equal to C log 10 1 into R, D is equal to S is equal to, sorry, D, option D, S is equal to C log 10 1 minus R. Answer B is the correct one. So why the general form of the log transformation given by S is equal to C log 10 of 1 plus R, where as we know C is a constant and it is assumed that R should be is greater than or equal to 0. So what will be the third question? So third question here is what is the general form of representation of power law transformation? So as we all know which is the correct answer for this. So that is given by S is equal to C R to the power of gamma. Yes, that is the power law transformation. So it is the basic form for that is given by S is equal to C R to the power of gamma, where uh, C and gamma are positive constants. Sometimes S is equal to C R to the power of gamma is also written as S is equal to C of R plus epsilon all to the power of gamma to account of an offset that is a measurable output when the input is 0. So what is the next question? um, Multiple choice question. So that is what fourth one. What is the name of the process used to correct the power law response phenomena? What is the name of the process used to correct the power law response phenomena? So options are beta correction, alpha correction, gamma correction, pi correction. What is the answer? It's a gamma correction. So that is what option C. So as we know, a variety of devices used for image capture, printing and display respond according to a power law. By convention, the exponent in the power law equation is referred as gamma. The process used to correct these power law response phenomena is called gamma correction. Okay, so the next question, which of the following transformation function requires much information to be specified at the time of the input? So that is what? Piecewise transformation. So options, log transformation, power transformation, piecewise transformation, linear transformation. So definitely we're going to choose piecewise transformation because the practical implementation of some important transformations can be formulated only as piecewise functions. The principal disadvantage of piecewise function is that their specification requires considerably more user input. So next question. In contrast stretching, if R1 is equal to S1 and R2 is equal to S2, then which of the following is true? So I'll read out all the options. The transformation is not a linear function that produces no changes in gray levels. The transformation is a linear function that produces no changes in gray levels. The transformation is a linear function that produces changes in gray levels. For last option, the transformation is not a linear function and that produces changes in gray levels. So which one is the correct one? It's a option B, because transformation is a linear function you're going to get when R1 is equal to S1 and R2 is equal to S2. Okay, so that produces no changes in the gray levels. So next question is the seventh one. So in which type of slicing, highlighting a specific range of gray levels in an image often desired. So what you're going to highlight? A specific range of gray levels in an image often is desired. Is it a gray level slicing, bit plan slicing, contrast touching, or byte level slicing? You also know that the answer for this is a gray level slicing, because where you're going to highlight the range of the gray levels. So you know the gray level slicing can also be called as an intensity level slicing. So applications here, it will include enhancing features such as masses of the water in satellite imagery and enhancing flaws in X-ray image. So the eighth question, highlighting the contribution made to total image by specific bits instead of highlighting intensity level changes is called, I'll give the options, intensity highlighting, byte slicing, bit plane slicing, none of the mentioned. So what is correct one? It's a bit plane slicing, because there is no byte slicing, right? And intensity highlighting. So we're going to have the bit plane slicing. So next question for our discussion. So which of the following involves reversing the intensity levels of an image? So which is one? That is what? The option image negatives. So I'll give the options. So that is what? Log transformations, piecewise linear transformations, image negatives, none of the mentioned. It's image negatives, because image negatives use reversing intensity levels. Okay, so our 10th question is, piecewise linear transformation function involves which of the following? Bit plane slicing, intensity level slicing, contrast touching, all of the above mentioned. What is that? You know already the piecewise linear transformation are of three types. So one is the contrast touching, intensity level slicing, bit plane slicing. So we'll go and choose the option D. So that is what all of the mentioned. Okay, so thank you. So this ends your session 1. So